So phase diagrams, we talked about how phase diagrams are limited in that when you are at a line, you know that you're having a state change, but you don't know how much time or energy it takes in order to make that state change. So this is where a heating curve helps. So a heating curve is taking a phase diagram at a particular pressure, so in this case, 1 atmosphere pressure, and I'm increasing the temperature and seeing what happens to my state of matter and also how much energy. So I'm transforming it into a temperature versus energy graph. I'm adding energy and it's causing the temperature to increase, and as a result, I'm seeing state changes. So this is a heating curve specifically for water, 1 atmosphere pressure, and you know this because the melting point for water and the boiling point for water at 1 atmosphere pressure is 0 degrees Celsius and 100 degrees Celsius. So this shows with the lines, oh, during this phase right here, I am in a solid state, and as I add energy to the system, my temperature increases. Once I get to the 0 mark right there, I go through a phase change, and I'm melting. I'm transforming my substance from a solid to a liquid. During this entire time, on this point, the temperature does not change. So similarly, if I'm transforming this into a heating curve, as I add energy, the temperature doesn't change. Once I have changed everything over to a liquid, now energy that is added to it will increase the temperature of that liquid until again it hits the boiling point, at which point the temperature does not change at all until everything has transformed into a gas. Remember that when I'm going from region to region on a phase diagram, this is all liquid, this is all solid, so on this line, this is where that transformation between solid and liquid occur. And similarly, this region is all liquid, this region is all gas, so while I'm at that point, that's the only time in which I can have liquid and gas present. Once I'm done transforming, then I can increase the temperature. So this does not show you what this shows you. This shows you that it takes energy to increase the state change from solid to liquid, and during that time there's no change in temperature. And again, this line tells you that it takes energy in order to transform from a liquid to a gas. So again, this is at a particular pressure. If I took this at a different pressure, I would get a different heating curve in that my melting point would be at a different temperature and my boiling point would be at a different temperature. If I took it at a much lower pressure, I would only have one line, and I would make the transformation all the way from a solid to a gas at that temperature. So a couple of things about this heating curve. You'll notice that the line segment for boiling is longer than the line segment for melting, and that should make sense. So remember that a solid is when your particles, your molecules, have maximum IMFs. They're having maximum IMFs, there is no movement, and so they're stuck together. If you're stuck together, you want to make sure that you're at your maximum IMF. So the analogy I have is when you're getting ready to sleep at night. So sleeping, you're going to have the lowest kinetic energy of the day. You're not moving. So your comfort is important. And so oftentimes it takes a while for you to get really comfortable. And it's not until you're really comfortable, maximum intermolecular forces of attraction, that you can then fall asleep. If there's something poking you, or if you're not quite in the right position, that you're going to wait until you get to that position. So molecules are the same way. If they're going to be stuck together as solids, they're going to maximize their force attractive and minimize their force repulsive. Gases, on the other hand, we define as having absolutely no IMFs whatsoever, right? So in order to go from a solid to a gas, I have to overcome all of my IMFs. If I have maximum IMFs, I'm a solid. If I have no IMFs, I'm a gas. Everything else is a liquid. So the barrier to becoming a liquid from a solid is really low. comparatively speaking. All I have to do is get the molecules to slide past one another. And it doesn't have to be fast, I just have to get them to slide past one another. And what happens is as the liquid heats up, you start to overcome more and more IMFs. So if they're moving very slowly, it's a viscous liquid. It's like molasses or something. As you heat up any liquid, it becomes less viscous. It becomes easier to pour. So think about honey or molasses. If it's really thick, you can heat it up and it slides past, it flows more easily because you're overcoming intermolecular forces of attraction. But when I'm trying to make that final leap into becoming a gas, I have to overcome every single remaining intermolecular force of attraction to become a gas. So that threshold is a lot higher. And as a result, it's going to take a lot more energy in order to overcome all of those IMFs to go from a liquid to a gas than it does to come over some of the IMFs to go from a solid to a liquid. So in any heating curve, and this is a generic heating curve, this line for boiling or vaporization will always be a lot longer. And this is reflected in the heat of vaporization. Heat of vaporization is a measure of how much energy it takes in order to boil something. And that will always be a much higher value than your heat of fusion, your melting value. Now let's look at the slopes of these lines. The slopes of these lines will tell you how easily the temperature increases for the amount of energy, right? So the slope is if I put in a little bit of energy and it increases a lot, that means that this substance is very easy to increase the temperature of. That value is measured by specific heat. So it's actually inversely related. So the higher the specific heat, the more shallow the line, meaning I have to input more energy in order to get my substance to rise as much. So you know that solids tend to conduct heat very easily. They raise their temperature very easily. And it's usually either because they are very rigid structures, like ionic compounds or covalent network solids, or they are tightly packed together, so if you wiggle one, it causes that kinetic energy to stretch throughout the whole thing, like metallic solids. So solids usually have a lower specific heat, so it's reflected in the slope of its line, which tends to be a lot steeper. Liquids tend to have a less steep slope. It's harder to get liquids to heat up, in part because as you move one molecule, this next molecule might move, but because there's already a sliding past thing next to each other, the molecule at the far side may not move as easily. So transmitting that kinetic energy, raising the kinetic energy with heat, is more difficult with a liquid. So the slope of the line for a liquid tends to be more shallow because I have to add more energy in order to get the same temperature change as it does with a solid. And a gas usually, again, tends to have a fairly steep slope. It's easy to increase the temperature of a gas, in part because all the collisions are completely elastic. So any change in overall kinetic energy is transmitted to everything.